Hello, I'm Anna Mackay and we're looking at the angle between two vectors. So this is what that would look like, and the vector on the third side of the triangle would be this one. And how do we define that? So you might think of it, so here's the start and here's the end point, that we're after negative A and positive B, and we know from previous work that we can write it in this order. Now, defining those vectors, we'll just do them in general terms of A1 and A2, B1 and B2. How would you find that length using other knowledge that you might have in maths? It's the third side of a triangle, but it's not a right-angled triangle, so you'd need the cosine rule. Before we get to that, we're just defining what a B subtract A would be, and noticing that the components are subtracted. So the B comes first, we've got B1 and we subtract A1. And then the second component is B2 subtract A2. So that defines that section. And as I said, using the cosine rule, that is the third side squared, and that's how we'd have to write this in terms of vectors, which corresponds to down here. And then it's this side, A side squared, so the length of these, adding on the B side squared, so the vector B, subtract 2AB cos theta. So we're going to have to work all that out. But first of all, we're going to prove that this is the case. All right, so here it is written out again. The first step we're going to do is to calculate the length, so the magnitude of vector B take A, so that was that third side, and then part of the formula is that you square that. So off to the right hand side here, let's work that out. So B take A, the vectors B take A, we want the magnitude of that, and the formula for that essentially comes from Pythagoras. So we've got a big square root, it's the B1 take A1, so that first term up here all squared, adding on the second one, square root over all of that. But for the formula that we need, as you can see, it's squared of that, so let's square both sides and see what we get. If you square the right hand side, that square root will cancel out, so you're just left with these two components squared. Alright, so the next step I want to do is to substitute this in for the left hand side of this equation and put it equal to the right hand side, and we're also going to work out what these components are. Let's do that. So for the left hand side, we're actually going to expand out now these perfect squares. So B1 squared here, and being a perfect square with a subtract, it's subtract two lots of each term, then the A1 term squared, and now we're adding on the second term here, expanding out that bracket. Now that's equal to the right hand side. Now what's this? This is the magnitude of vector A, and to work that out, it would be the square root of A1 squared plus A2 squared, and the square root of all that. But because the formula is telling us to square it, that square root and the square will just cancel themselves out, so we are left with the A1 term squared and the A2 term squared, and the same thing applies for the B here. And then the final part is to subtract off this. We're just going to leave it in that form for now. As you can see, I ran out of room a little bit there. Let's see what might cancel out. So on the left hand side here, we've got a B1 squared, and on the right hand side, we have a B1 term squared. So I'm just going to cross out the things that will cancel out. We've got that, as I talked about. Another term we've got is the A1 squared, one on each side. We've got an A2 squared on each side, and a B2 squared on each side. So they're all cancelling out. Now have a look what we're left with here, here, and here, that whole term. Notice that they each have a factor of -2, so we're going to divide through by that, and I'll write out what we're left with. In this first term, we're left with the B1A1 term, but we know that we can write them around the other way in numerical order. So I'm writing that, and now I am adding on this term here, and that's equal to the right hand side of this, cos of theta. Now you might recognize that on the left hand side here is equivalent to what formula that we've established in a previous video. It's the dot product. So that is the same as A dot B, those elements of those vectors multiplied together. We'll put that equal to the right hand side, and therefore we can rearrange for cos of theta. So this is now giving us the formula for the angle between two vectors. And that is the proof of that formula. All right, so summarizing it here, this is what we have. Rearranging, as you saw in the other slide, and remembering that the dot product is those elements multiplied together and then added. If those vectors are perpendicular to each other, imagining what they would look like as such for vector A and B, now the angle between them is what? 90 degrees, and we're after the cos of 90 degrees. If you followed me for the work on the unit circle, cos of 90 degrees, cos is the x component. Therefore, the x component at 90 degrees is 0. So cos of 90 degrees would be 0. And what impact does that have on the formula here? That means the dot product of those is 0. And if you therefore get that, it is, confirms the rule that they are perpendicular to each other. That applies for non-zero vectors of A and B. Now, if they're parallel to each other, what would the angle between them be? If they look like that, for example, that the angle between them would be 0. And the work on the unit circle of what value of cos would you get for an angle of 0? You would get 1. So that therefore means, thinking about up here, that if cos of 0 is 1, that the cos part is just 1, and so therefore this is it on its own. So therefore the formula also in that case is equal to this, so that the dot product is equal to the magnitude of both of those vectors. And same for if the angle is 180 degrees, you think about what the cos of 180 degrees is. If you've done work on the unit circle, it's -1. And so therefore the formula for that looks very similar, but just with an extra negative. Just writing that out, that if they're equal, by default, it means they're parallel. So if you establish that fact with a particular question, it's equivalent to the fact that they are parallel. Just in terms of which direction they're going, you'll have to see if it's negative or not. If the angle between them is acute, again, work on the unit circle would say that cos of theta is therefore greater than 0. You would get a positive x component, and therefore the dot product is greater than 0. So positive. Now, if that angle there is obtuse, that therefore means that the cos angle is going to be less than 0, the cos of the whole angle, and therefore the dot product is less than 0, a negative number. And that the angle that we're dealing with, we have between 0 and 180 degrees. We don't do the reflex angle because we're after the angle between two vectors, not on the outside or where it's red is what we're after. Okay, doing some examples now. So if we're asked to find t such that vector A and vector B are perpendicular, how could we find t? So the fact that we've got is that if the dot product turns out to be 0, that means the vectors by default are perpendicular, and that will help us work out what t is. So the way I would set this out is that if the dot product of A and B is 0, I would write my vectors with square brackets because I find that easier to work with, each to their own though. And then I'm going to do the dot product of those. And so you multiply corresponding terms, so what's in the first position of each, and then we're adding on the second terms multiplied together, and we're saying that if they are perpendicular, that dot product will be equal to 0. So then we rearrange and solve for t. So t has to be 2/5 if they're to be perpendicular. Next one, if we are to consider these points, and we're asked to use the scalar product to determine whether triangle ABC is right-angled, and if so, find the right angle. My suggestion is whenever you're doing these sorts of things, create a visual, create a picture if you can. So these are these are coordinates. So what would they look like? So if A was 2, 1, so you could draw a Cartesian plane. So I might imagine that the origin is there at that first dot. We're going across 2, up 1, and I'll put A there. B then would be across 6, down 1, and C is across 5 and down 3. So now we can see what these would roughly look like. Here is our triangle, and where would the right angle be? Of course, drawn with a ruler, the right angle would be at B if there's a right angle there. So we need to work out vectors A to B and B to C, and then we can do the scalar product of those. So vector AB, to work that out, you take the B component first and you subtract off the A component, and then we do -1 subtract 1, And our answer for that is 4, -2 for the vector AB. Second one, let's do BC. Noticing that's +1 there because we have to subtract off -1, and that leaves us with -1, -2. So now we want to use the scalar product. I've been calling it dot product as well. Put those two next to each other, and to be right angled, what answer should we expect? That they are perpendicular, so we would expect an answer of 0. Let's see if we get that. So of these two vectors here, we multiply the components and add them. Working that out, we have -4, add 4, and yes, that's equal to 0. So then we would say that vector AB is perpendicular to vector BC, and that triangle ABC is right angled at angle ABC. That's how we answer that one. If we're asked to find the form of all vectors perpendicular to vector 3, 4. When vectors are perpendicular to each other, we've got this fact here that if you've vector AB, therefore the elements, what do you notice? They've switched positions and one of them is negative. Or the other way here, they've switched positions and the second one is negative. I like to create a visual, if I can, a picture of what we're doing. So let's draw a vector 3, 4. So you pick a starting point and we're going, pick a starting point there, we're going across 3 and up 4. So with a ruler, this is what this vector would look like. Let's check this. What would it be if it's perpendicular then? So this fact up here is telling us to switch the positions so that you would then have a vector that would be 4, 3, and one of them is negative. So, oops, square brackets. So let's say a -4. So from this same starting point, let's go left 4 and up 3. And using a ruler, connect them. Do you think that looks perpendicular? I'd say so, pretty close to it. And so that confirms this rule about switching the positions and one is negative. Let's mathematically work that out now. Finding vectors of the form. I've gone on to part B as well, but we'll just do it all in one go. So first of all, we have to work out the dot product and find that they are perpendicular. The dot product of that is -12, add 12. The scalar product is 0. So they have to be of the form where it's a scalar multiple of that perpendicular version, and k must not be equal to 0. So vectors of the form k is not equal to 0 are perpendicular, that's that symbol there, to 3, 4. I haven't written that in a very straight line, but I'm sure you can work that out. Then part B is asking us to find a vector perpendicular to 3, 4 of length 3 units. So to do that, that should be a key that you need to work out the unit vector. So first of all, we need to know the length of this vector, the perpendicular one. So we want the magnitude of this, the length, and using our formula for that. So we get the square root of 16 plus 9, which is the square root of 25. So that's equal to 5. Now, k is the scalar, and so if k is 1 over the length of that vector, that would be what we need for a unit vector. See the previous video on unit vectors if you need some refreshers on that. And therefore, reading the question, a vector of length 3 units, so what would that look like? So we want 3 lots of that unit vector, so 3 multiplied by a fifth, so we can go 3 over 5, and then you put that, that's the scalar multiple of that perpendicular vector. You could leave it like that, but we often tend to bring in that scalar. And so to answer the question, find a vector that is perpendicular to the vector 3, 4, and it has length of 3 units. That's our answer for this one. Join me in the next video, and it's a continuation of this video with a few more examples. Thank you.